All right. So can you see the screen? Is it visible?
Yes.
All right. Okay. So last time we were talking about energies of a simple harmonic motion, right? So is there any question regarding that? The how does the kinetic energy, potential energy vary with the displacement of an object that is performing or undergoing any oscillations? And then we saw how the total energy would be a constant, right? And so it would have looked something like a straight line. Why is that not forming straight? Okay, so something like this, right? So this is what it would look like if I were to plot the total energy, because the sum of potential and kinetic energies would be a constant, right? So, and this is how the kinetic energy and the potential energy looked like, right? So this is the kinetic energy and that's the potential energy. So the potential energy, because of the conservation of energy, where the kinetic energy is maximum, the potential energy has to be a minimum, while where the kinetic energy is minimum, the potential energy has to be maximum, right? So these are the variation of kinetic and potential energies with displacement, while this is the variation of, well, not variation because it's a constant, but a graph shows the how does the total energy depend on the displacement of the pendulum or any oscillator. Right. So now let's talk about some of the equations, right? Or the solutions of a simple harmonic motion. What does that mean? That means that, remember, I talked about this equation, m d squared x by dt squared, which is equal to minus kx, right? This is the restoring force of any oscillatory motion, while this is just the Newton's law, Newton's second law, right? Which is ma. So this little thing, derivative of the x with respect to time, 2 times this derivative is this thing is the acceleration, right? So this is this type of an equation is called an ordinary linear differential equation, right? And you can work out the solutions to these type of equations. We are not going to do the mathematics of all of that. It's sufficient to know that the solution of this type of an equation, well, from expectations, you would expect it to be a sinusoidal type of a solution, meaning a periodic solution, right? So something that keeps on a function that repeats itself. And we talked about those functions. They are sine and cosine functions, right? So if this is a sine, this is a cosine function, right? So these are the functions that repeat their shape after some intervals. So the solution should look like either one of those. So if the solution to this equation, is what we want, and that is that x is equal to, well, now this k over here is a constant that depends on omega, and the solution to this equation is cos omega t, right? Now cos, it could be cos omega t, or it could be x is equal to sine omega t. Any of these two solutions will work for this equation. Now, when I say that these two are the solutions to this equation, differential equation, what I mean by that is that any of these two solutions would solve this equation. Meaning that if I were to put in place of x in this equation, cos omega t, and even here I put cos omega t, I would get left hand side equal to right hand side. So it's a solution to this equation. Similarly, this sine omega t is also a solution to this equation. Now, if both of these are solution, we may pick any one, right? And we can do that because you know that sine and cos omega t can become a same function with some phase, right? So if I were to, for example, let's move this wave, this one, sine wave, slightly to the left. So that would look like this. So imagine I move this part of the wave to the left, so it would go over here, and it would look something like this. And then let's keep on continuing and so on. But now if I've just moved the wave to the left. Now if I look at things that are to the right of this line, now this function looks like a cos function. So just by moving the wave, meaning causing some phase change, I can change a function from sine to cos. So these two functions, they have each other in them built in, right? With some phase change. Now I can pick any one of these solutions. For our purposes, let's just say that the solution that we'll stick with or follow is x equals sine omega t. Now, for some purposes, we also have to put a constant over here, and we'll call that constant x naught, right? So it comes from the purpose of derivatives and so on, but that's more or less mathematics. So I'll not go into that. This much is enough, that this constant, there is this constant, and this constant defines the amplitude of oscillation, how high the oscillation can be, right? So the bigger this number, the bigger the height of the oscillation. So now, what just happened? Right. So now this is a solution with an x naught over here. And this thing is what? This is the displacement, because it's x, right? So it is the displacement of any type of oscillations. So you can fix a constant. Omega is just the angular frequency, right? 2 pi times f. And for different types of oscillations, depending on how fast the oscillation is, omega will be a fixed constant, right? And time period t is just the time interval, right? So at 1 second, 2 second, 3 second, and this will tell you what would be the displacement. For example, if I have an oscillator, then it will be oscillating, right? So it is displacing from its mean position to the left or to the right. So I can put some value of t after 1 second. What is the value of x? How further has it been displaced from the oscillator, right? So from its mean position. So that's what the displacement of the oscillation or a body in a simple harmonic motion means. Now, quickly remember that we have said this, we have seen this, that the gradient or the derivative of position, if I take the derivative of this thing, or you can just say taking the gradient of x, right, with respect to time, is the velocity, right? Everybody agrees with this?
Yes.
The gradient, right? Okay, the gradient of the position or the displacement is velocity. So if I were to take the derivative of this function x with respect to time, then I would get velocity, right? And so let me just quickly do this over on the next page. Uh, I'll call this thing a relation between displacement and velocity. Now, we know velocity is just the time rate of change of position, right? So for those who do not understand derivatives very well, just these derivatives are just saying that they're the rate of change of something. So d delta x by delta t, meaning x2 minus x1 divided by t2 minus t1. This much is can be enough for your understanding. Uh, Once you have trigonometric functions, I think I've talked about this, the derivative of a sine function, suppose it's sine omega t, if I have a constant over here and the variable with which I'm derivating this function, the derivative of sine is itself cos, and the variables will be the same, cos omega t, and this omega comes outside, right? So this would be omega times cos omega t. Similarly, if I take a derivative with respect to t variable of a cos function, cos omega t, then the derivative of cos is minus sine, and omega t will still remain the variable. And this omega, the constant with which I'm not differentiating, that would come outside. So omega multiplied by minus sine omega t, which is minus omega sine omega t. So just know this thing, right? If you know this thing, then now remember quickly that x was x naught sine omega t. Then to find velocity, I just have to differentiate this with time, meaning this would be d by dt of x naught sine omega t. X naught is just a constant number. So the derivative is with respect to time. So the time x naught does not depend on time. It is the maximum, it is the amplitude of the oscillation, right? So it will always be the same no matter what time it is. So I can just write this outside. The operator will not act on it. And now we are left with sine omega t. And we know from this thing that on sine omega t, it acts like this. So this would be omega cos omega t. All right, so is that clear? Is that clear? Is everyone following along? Okay. All right. So now I'll send you these notes, right? Do this as an exercise. Relate v, velocity, and displacement, right? Relate them. Hint, I'll give you a hint, right? By using this thing that sine squared omega t plus cos squared omega t is equal to 1. This is a trigonometric identity, which is basically sine squared theta is plus cos squared theta is 1. If you use this, we know that in x, I have sine, in velocity, I have cos. So you can just square these two and add them together, right? And then you can use this relation to see the relationship between V and X. Do it as an exercise, right? Do it yourself and see if your answers match with what I'm going to write right now. The answer is velocity is equal to plus minus omega square root of x naught squared minus x squared. So this is a relation that relates the displacement of a body or an object with its velocity. So is that clear? I mean, it's very simple exercise that I gave you, right? Just a two-step solution, and you can do it and see if your answers match. The reason I'm giving some exercises is because you should also be doing something after the class is over, right? And then we have the velocity. Now, the reason I was looking for velocity is I want to write down the kinetic energy of the oscillation, right? So the kinetic energy of the oscillation can be written in terms of velocity, because I know that the kinetic energy is half mv squared, where m is the mass of the system that is oscillating, v is the speed with which the system is oscillating. And so now I just plug in the value for v that we found over here, and the kinetic energy of such a system is half m. And if I square this thing, then the square of minus, we have plus minus, right? So plus square of plus would be plus, but the square of minus would also be plus. So the sign just becomes a positive sign, and we have omega squared, and then the square of this thing will cancel the square root over here, and so we are left with x naught square minus x squared, right? And so the kinetic energy is half m omega squared times x naught squared minus x squared. So was this clear? Is this clear?
Sir, can
Yes.
you explain that x naught part again?
Which one?
Where, yeah, from here above.
Or I mean, can you be a bit more specific from what part are you asking?
Like where we involve x naught in our equations.
Oh, x naught is just the amplitude of our oscillations, right? So let me come back over here. So we started with this thing. This was the differential equation of a simple harmonic motion, where this first term is just Newton's second law, ma. This thing is xa, acceleration. And Newton's second law, this thing is equal to the restoring force. Whenever you have an oscillation, then there would be some restoring force. And so this thing is equal to minus kx, the restoring force. Now the solution to this type of an equation is this one. X is equal to x naught sine omega t. X naught is just a constant, and that constant carries the units of meters or whatever are the units of x, meaning that it is just telling you about the amplitude of any oscillation. So for example, if you consider a pendulum, and if a pendulum hangs like this, I displace it to some height and then release it. So it's going to start oscillating like this, right? And it's going to come back to this height. This height is the amplitude, as you all know. And so this x naught is just that amplitude, right? Now, we know from here, the next thing was velocity and displacement. We know velocity is just the derivative or the gradient of displacement position, then all I have to do is to take the derivative of x equals x naught sine omega t with respect to time, and I'll get velocity. And the derivative of this position x is this thing, x naught cos omega t. So from there, then we can use, I gave this as an exercise, do this yourself. Use this sign, this identity, sine square theta plus cos square theta is equal to 1. You can see that in x you have sine, in v you have cos. So if you square both of these things and add them together, then you can find this relation, right? And then when you find this relation, then just use this in half mv squared. In place of v, use this thing, and then you get the kinetic energy as this. So x naught is just the amplitude of the oscillation. It will always be a constant number. The only variable in this is x squared, right? So it is any position of the oscillation. Is it clear?
Yes, sir. And sir, the omega becomes square when you involve it in the kinetic equation, right? So how is that?
Yeah.
Because
No,
above it is in the form of square normal constant, right?
yeah, it's still a constant. Omega is still a constant. It becomes squared, right? Because omega really is angular velocity, right? If we have studied circular motion, and we know that omega is an angular velocity. If something is moving in a circle, suppose like this, then it will have two types of velocities. One was this tangential velocity v, and one velocity is this velocity with which it is moving in a circle, and that is omega. So omega is also a velocity, and you would expect it to be squared in the expression for kinetic energy, because in kinetic energy, anything that is a velocity must be squared, right? So it just becomes squared. It's still a constant, meaning it's that value with which the oscillation is oscillating, meaning remember its omega is 2 pi times f. F is nothing but 1 over t, so this is something like this. Now 2 pi is in radians, and this 2 pi means a complete angular displacement, right? So this is angular displacement theta, so it is theta by t. In circular dynamics, theta is just as how position is in linear dynamics, and this t is still a time period, time. So this is position divided by time, and that's velocity, right? So that's omega. Now in our motion oscillations, if something is oscillating, and we have not talked about damping as of yet, as in the oscillations start decreasing. We have not talked about that. We will after this thing, but so omega will always be a constant as long as there is no damping in the oscillation. So for what I'm trying to say is, suppose if I have this pendulum, if it's oscillating, so far what according to what I'm talking about, this pendulum will keep oscillating forever. But in reality, that's not the case. In reality, the pendulum will oscillate, then slowly its amplitude will start decreasing, right? So now it will move even less to there, and then even less, and then even less, and then eventually it will come to a stop, right? But so far right now, omega is a constant, and this is the kinetic energy of the this type of oscillations. Is that clear? Is it clear?
Yes, sir.
All right. Okay. So you see how much we have time. Mm. Okay. So that's kinetic energy of the oscillations, right? If there is any question, feel free to ask. Otherwise, I'll move towards the potential energy, and then we can start talking about damping, right? By the way, what do you think would be the maximum kinetic energy? The maximum kinetic energy of the system is when, for example, a pendulum is crossing its mean position, right? And at mean position, displacement is 0. So when a pendulum crosses its mean position, that's when it has the maximum velocity. And at mean position, displacement x is 0. So in this equation, in place of x, I'll just put 0. So I'll be left with 1/2 m omega squared x naught squared, which is what you should expect, because x naught is the amplitude of the oscillation, meaning it is the maximum height of the oscillation. So the maximum kinetic energy will, a system can gain the maximum kinetic energy when it's raised at some maximum height, so that all that potential energy will be converted into the kinetic energy, right? So that's the maximum kinetic energy of the system. Then we can now talk about potential energy of a system, of an oscillatory motion. And that's a simple potential energy. We know it is E is equal to half kx squared, right? Any system that is oscillating will have this elastic potential energy, and k is nothing but m omega squared, right? The value of this constant is m, which is a constant, omega squared, which is also constant. So k is defined as this thing. And now E becomes half m omega squared x squared. But remember, what was x? In our solution, x was defined as x naught sine omega t. Then you can further go further to write this potential energy as half m omega squared x naught squared sine squared omega t, right? So these are two expressions that you can use for potential energy, right? Let me just go back, and I used k for kinetic energy. Let me use ke, because then you might be confused when you look at the notes. You might confuse k for the constant, right? Which is this constant k in this expression. So that's how you can write down the potential energy of such a system. So is that clear? So this is the potential energy. Then the total energy of the system is simply the sum of the two, right? Total energy is kinetic energy plus potential energy. So that means the total energy T would be kinetic energy, as we saw, is this thing, right? Half m omega squared x naught squared minus x squared, right? So half m omega squared x naught squared minus x squared, and plus potential energy, which is this one. So it is half m omega squared x squared. So I can just factor some things out and write it as half m omega squared times x naught squared minus x squared plus x squared. So you see that these x squareds cancel out because one is plus and one is minus. and the total energy of the system is half m omega squared x naught squared. All right, so is that clear? Any questions?
No.
All right. So are things clear, right? So you're not getting confused. If you are, feel free to let me know, right? If there is anything that you do not understand, if there is any confusion of any sort, just feel free to stop me and just ask if there is any type of confusion. Anything that you do not understand, because of course you're taking a course, and so you should you have this facility of asking your questions, so feel free to ask your questions, right? Okay, so if there is no question, then we'll do a problem now, a fairly simple problem that has to do with these energies. Let's take an example of a pendulum, right? And so we have a pendulum and it's oscillating, right? It's oscillating. And this mass, which is attached to a pendulum, I'm going to write it here, is 200 grams, right? And suppose I take the maximum height that I raise it to, which is the amplitude of the oscillation, x naught, is 2.5 centimeters. So that's the maximum height that I raise the pendulum to, meaning that that's the amplitude, right? So here I'm just telling you the wordings of a question in your exam. So the maximum height that the pendulum raises to is 2.5 centimeters, meaning maximum height as in the amplitude of the oscillation. Or let's take it 5.2. 2.5 is very small, right? So 5.2. Now, once you do this and you release the pendulum, it goes over here like this, and then it comes back to like this, its original position. That's one oscillation. And suppose you time that and it comes out to be 2 seconds. In 2 seconds, it does this oscillation. Our question is to compute the maximum kinetic energy, right? So to compute the maximum kinetic energy, or that's the question, right? So that's what we want to find. But I want you to tell me at what point in time or at what point in this figure where will this pendulum or bob have a maximum velocity, because that's when it will have the maximum kinetic energy, right? So where would this pendulum, this ball, where would it, at what point in this swing, right? It's swinging in these directions. At what point will it have maximum velocity? Anyone?
Where its potential energy is 0.
Yes. And where would the potential energy be 0?
When the string is straight.
When the string is straight. So at the center, right? Over here. Right. So this position is also always called the mean position. So the potential energy is always 0 at the mean position, and mean position, right? So I'll write it over here. It's MEAN position. And if the potential energy is 0 at this position, then the kinetic energy is maximum. So when it's crossing this point of mean position, it will have the maximum speed that it can possibly have. So I need to find the velocity at this position. Now, let's try to find that, right? We can find that by, if we know the kinetic energy, the expression for kinetic energy, maximum kinetic energy, it was, if you go back, we wrote it down as this thing, right? Half m omega squared x naught squared. right? This thing. Now, if this is the maximum kinetic energy, then let me write it half m omega squared x naught squared. If you remember from your circular motion, we saw we could relate v and omega, and that was by v is equal to something like position r and then omega. Now in this case, r is just that x or x naught, right? So this is v is equal to x naught omega. Now if I square both the sides, I get v squared is equal to x naught squared omega squared. So I can replace this thing with v squared, and so I just get half mv squared, and I just want to find the value for v, and I have to figure out the maximum kinetic energy. Apparently we have just less than 1 minute remaining, so the class will end anytime. I want you to note down this homework, or I'll share this thing with you. Do this thing, find v and x relation between these two.